So if you are looking at the bomb calorimeter, that is when you use a bomb calorimeter to measure. Remember I was telling you the food sample is dropped. Do you remember me saying that? The food sample is dropped inside, right? It's dropped inside the chamber, and then you will have your food sample burnt, and the water surrounding. So do you see how the thermometer is in the water? It's dipping inside the water. Do you see that? So it's only the temperature of the water that you measure. Most of the foods we eat are exothermic, right? So you expect the water chamber to heat up. And that's why for these bomb calorimeter samples, you're not looking at how much food sample you take. You're looking only at the amount of water that is taken to do the problem. Okay, so if you're, did we do these problems already? Did we look at a question on glucose?
Not yet.
No. So let's try and do this. 1 gram of glucose was burned in a bomb calorimeter. 1.25 times 10 to the 3 grams of water. Now that's the mass of solution. MS will just be the mass of water. Is that making sense, folks, in the formula? And it was warmed from 24 to 31. I remember correcting that. It's 31.5, not 1.5. I told LOH 206 downstairs. Okay, and this is the formula. Q equals MS times delta TS times FH. Yes? The mass of the solution, you will plug that in. Temperature difference is 6.1 because you subtract 24.5 from 31.5. And the specific heat is 1. Does that make sense to you all, please? You plug it all in, and you will get this calorie. But again, remember, we're converting it to nutritional. Do you remember me saying what is nutritional calorie? Yes, it's a kilocalorie, or 1,000 of the small calories, yes? 1,000 of the little c calories. So you will convert that, and then I need you to understand one more thing. So nutritional calorie, write this down, nutritional calorie is the same thing. It's also represented with a capital C, which is the same thing as kilocalories. Okay, it's also sometimes written with a capital C. Now, when the problem asks you for fuel value, when it says what is the fuel value, you must take this big C calorie and divide it by the mass of the food sample.
Wait, the big C cal is the same as K cal?
Yes. The big C is the same as the KC, the K little c.
Oh, okay.
Does that make sense? So fuel value is, this is the unit for fuel value. Calories per gram of the food. So when you go back to your this question is not complete. All we have right now is nutritional calories. But if you go back to the problem, it asks you for calculate the fuel value. Do you see that? So what you have to do is take the 7.6 nutritional calories and divide it by what? The 1 gram. Did you follow that, everyone? And so in this example, because it's 1 gram of glucose, the answer is not going to change very much, is it? It's still going to be 7.6 nutritional calories per gram. Did that make sense? Okay. Then in that case, I'd like you to do one more problem. And this problem will probably be something you can relate to. I want you to look at problem chapter 7. Okay, I want you practice problem 7.5, page 238. Practice problem 7.5. Okay, practice problem 7.5, page 238. If you look, because yes you do, because it says calculate the fuel value, which will be nutritional calories per gram, right? But it also says, and the total caloric content of the whole bar. So in other words, if you ate the whole bar, how many calories will it release? So you do need the mass of the whole candy bar for that. Okay, so let's do this problem in steps first. First thing, just find me the nutritional calories. Well, how do you find the nutritional calories? What formula are you going to use? You're going to start off always with Q equals what? Mass of solution times specific heat of water times delta T. Is that what you all are doing to find the nutritional calorie? Okay, what is the, now I told you, for a bomb, it's not the mass of the sample. What are we looking at? Yes, the mass of the water. Do they give you the mass of the water? What is it? Plug it in. 1.00 times 10 to the 3 grams. What's the specific heat always of water? 1 calorie, right? Times, what's delta T? 3 degrees Celsius, correct? 3? No, we don't, because if you look, the units for specific heat are gram and degree Celsius at the bottom, correct? The gram cancels with this gram, and the Celsius cancels with that Celsius. Is that clear so far? So now finish off the math, please. 1 times 10 to the 3 is 1,000 times 3 is what? 3,000. But is this small c or is it the big C? This is the small c. Now what did I tell you I need for nutritional calorie? The big C, right? Or the kilo. So convert it to kilocalories. Did you get it? Did y'all get it? How do you convert it to kilocalories? Yeah. You take the 3 times 10 to the 3 little c, and you would have to divide, because 1,000 of the little c is in 1 kilocalorie, correct? So you have to divide, not multiply by 1,000. And you will see that 10 to the 3, we only found the little c. I want the big C, which is the same thing as the kilocalories. No, the other way around. 1,000 little c's make a big C. Right? Or just remember the conversion unit. 1,000 calories make 1 kilocalorie. That makes sense, folks? Like 1,000 meters make a kilometer, 1,000 grams make a kilogram, so on and so forth. A kilo stands for a factor of 1,000. So what is this? So final answer is 3 kilocalories, or I could have just as well said capital C. Is this clear so far? Now, that's not what the problem is still asking. We're getting to the answer, but we're not there yet. The problem says, what is the fuel value? Now, what did I say you need for fuel value? Divide by the grams of the food sample they burned. How much of the food sample did they burn? 1 gram. Is that making sense? So, you take these 3 kilocalories and you divide it by 1 gram of the food sample. That is fuel value. Okay? Do you see how they took 1 gram of the candy bar? So this is what we would say is the fuel value that the problem is asking. Okay? But they're asking another question. What else are they asking? No, they're saying, yeah, and they're saying calculate the fuel value, but also calculate the total caloric content. How are you going to do that? Do you know the mass of the whole bar? 2.5 ounces. Now, you have 3 kilocalories is what you're going to get if you eat 1 gram. So what is it that you need? You need the mass of the whole bar in grams. They don't give it to you in grams, but they give it to you in ounces. So we go back to chapter 1, where we need to convert ounces to grams. So you see why chemistry reviews are meaningless, because if we don't know chapter 1, we could very well be on chapter 7, and it won't matter because we forgot how to do dimensional analysis. See what I mean? So you need to convert 2.5 ounces to grams first. Does that make sense to you? 2.5 ounces, and I need a conversion factor between ounce and grams, which means you need to go back to your book to tell me what it is. I'm sorry, 16? Or go to the very back flap of the book, the hardcover portion. Sometimes they have conversions over there as well. Oh, 16 ounces is a pound. And what did you say, 454 grams is a pound. This is a great conversion problem. Did you all hear? Okay, I'm going to give you both. 454 grams is a pound, and 16 ounces is equal to what? So tell me, what conversion factor can you use? Yeah. So you could very well say 454 grams is 16 ounces. Yes. Yes, you could use that conversion. Does that make sense? Okay. Yes, is that what y'all did? You convert, you cancel ounces, and you should get the answer of the bar in grams. What is it? 70.9 grams. Yes? That's the mass of the whole bar. Now tell me, if you ate 1 gram of the bar, how much energy was being released? Correct, 3 kilocalories. So if you have 70 grams and you eat 70 grams of the candy, how much energy will you release? Yeah, you're going to say, is that making sense to you? You're going to say, you're going to start with 70 point, what was the grams of the bar? No, 70 point what? 9. So you're going to start with 70.9 grams, and you're going to say every gram of the bar you eat releases 3 kilocalories. If I ate 70 grams, is this making sense to you all or no? No, 70.9 grams is how much you're consuming. But if you consumed a gram, you'd release 3 kilocalories, correct? For 70.9 grams, you would release how much? Is that making sense? So imagine 212 kilocalories. Oh, wow. 212 kilocalories per bar.
So when they give us like the calories on the soda and stuff, they're doing regular calories? Or they're doing
No, they say nutritional calories, don't they? They say nutritional calories. So that's why you're learning this, because nutritional calories is not the regular calorie. Nutritional calorie is what? K-calories. It's kilocalories. Yeah. To get the little c, yeah. Yeah. That's a lot of energy. That's why you feel pretty full after a bar. Even though it might be all, now whether all these calories are good for you, there's a lot of junk calories, right? Because it did say that the bar is full of sugar and fat. Sugar and fat just gives you empty calories. They're not good for you.
So, the place I was for what we should save in the class, not kilocalories, or kilocalories.
What is the what
What
income?
would you say for an average person, how much should we take in for calories? Because I know they say like 2,000.
Yeah, yeah, it depends on your weight, but they say about 3,000.
3,000.
No, that's now they say that's excessive. But again, for women and men, it's different. For women, it's about 2,000 calories. Yeah, it depends on your activity level. If you're an athlete and you're running and you're very active and you burn a lot, then they say about 2,000. So for people who are not doing all that, it should be more like 1,500. And for men, it's about 2,500. Again, if you're very active, if not, it should be a little less. But again, it all depends on your height and weight also. The fact is, we're all overeating. We are. Yeah, and then if it's good or bad, right? So we're all over. And then so if you eat a lot of good calories, then you're likely okay, like nuts and almonds. So you could get a lot of calories from eating just a small portion of nuts, but nuts are good for you, versus this candy bar, which is a bad choice. Absolutely. You always walk on the side of natural, you're likely to be okay. Even if you binge. You're okay binging on vegetables. You're not going to gain weight binging on vegetables. But try selling carrot as a snack. How many people like it? Oh, well, that's good to hear.
But celery has negative calories.
Because it's more water. Yeah, which is good because it fills you up for the short run. So they say consume those. And it has a lot of fiber though. It has a lot of fiber. Ma'am. A high protein diet is always good for you because you feel satiated for a longer time because your stomach is at work. When your stomach is occupied and it's breaking things down, it doesn't send the signals to your brain that you need to eat. So being satiated for a longer time is a good thing. The problem with carbs is they're addictive because sugars, but you feel hungry more quickly, right? With sugars, you feel hungry because you're satiated for a shorter amount of time. Because it's very easy for the body to break it down. It goes into your blood more quickly. But they say when you're diabetic and if you're dying, I mean not dying, but if you're diabetic and you're feeling very dizzy, have sugar. That's the first thing you should have because it enters your bloodstream more quickly than protein. So see, for all you budding nurses, I know just it's early going into nursing school, but many of you are, right? These are things you should be able to, because you might end up having to consult patients on nutrition. And in San Antonio especially, there's an important need for nutritional discussions. So, anyway, moving on, next thing. Okay, so that's all we do with thermodynamics. Now we go into kinetics, the second part of chapter 7. Kinetics is, so thermodynamics tells you, will a reaction take place? Kinetics will tell you how quickly. Okay? Now there are portions of kinetics that I'm not going to cover. I'm just going to leave it out and I'll tell you which ones. But kinetics, okay, start. Load content. So I hope to finish 7 today. I hope. We'll see. Or maybe definitely Monday. In which case you should have a quiz opening up.
Have you changed the due date for the paper?
When is the paper due? Did we? Yeah, no, I'm going to change it. I'm going to change the due date on the paper, yes. I have to do so much. Oh my God, I better remember to do all this.
I have a question about that. For the guidelines and everything, I was trying to find it to make sure that
Have you looked in Canvas?
I have looked in Canvas and I looked at your files.
No, modules.
Modules?
You must go only through modules, because if you do anything else, you're not going to find it.
Okay, because I was trying to look for it. But did you just have it in your peer review?
No. It's under reaction. So if you go here and you look at modules.
I'm sorry, I've been trying to look for it like crazy.
No, you need to go here under research paper, topic selection, guidelines, and grading rubrics. And everything about what to write is under selection, how you'll be graded is over here. Yes?
Okay, so research paper and rating, is that the whole thing?
You read, go ahead and read all 3 of these. Okay, only under modules, please. You shouldn't be going anywhere else.
Okay, thank you.
You're welcome. All right, now for the chapter. So, is the study of the rate or the speed. How fast, how quickly will this reaction take place? So if you look at all these beakers, right, there are 4 different kinds of beakers. How do you tell whether a reaction is taking place? Well, you look for color change. You can look for heat development. You can look for precipitate. You can look for, like, look at this reaction. It went from deep orange to colorless. So you measure the color in this one, you measure the color in this one, and this one, and this one, and you can tell how much of the concentration has decreased depending on the color, right? Now, for reactions to even take place, there are some. So you need to know the definition of this term. What is an effective collision? An effective collision is one in which the bonds will break. Because remember, these guys are bouncing around with each other in the air that you breathe every day. Methane and oxygen. There's plenty of that in the air, but they don't always break and form carbon dioxide and water because you don't have the energy to break the bonds. So effective, okay, this is an ineffective collision, okay? A collision where they're just bouncing off very lightly. Like the ping pong balls that you throw at the window, are you likely to break it? That's an ineffective collision, but a baseball with the right energy will shatter the glass. And that's the kind of energy we need to break bonds. Okay? Now, what kind of reaction is this? Is this exo or is it endo? Exothermic, very good. Energy is a product. Yes? Energy is a product. So now for the activation energy discussion. Now remember, for every reaction to take place, there is and this is the hump. For some reactions, the hump is so steep, so the collisions that they have to meet this threshold. It is the minimum amount of energy required for a reaction to start. Activation energy is the minimum amount of energy that you need to provide for the reaction to start. Once it starts, it might maintain itself. Okay, that it can do. But if it doesn't even have the energy to start, then it won't take place. Like, imagine the best analogy I can give you is somebody climbing up, trying to get a boulder, right? So if you have a hill, it's getting that boulder up here. Once you get it over there, is it likely to roll down on its own? You see what I mean? So getting that boulder up there is the activation energy. Will that, once it gets there, will it stumble on its own? Yes. Did you follow, folks? For some reactions, this hump can be too steep, and for some others, it could be very, very gentle. Okay, it all depends. It all depends on the amount of energy it's going to take for the reaction to start. So there, activation energy and the complex. So when A and B are reacting, they're likely to reach this spot where they are both still together. And then the bonds break and C and D get formed. Is that making sense to you all? And notice another thing. C and D are at a lower energy than A and B. Always, always in chemistry, there is a driving force for why C and D should even form. Well, if C and D were more unstable than A and B, it would never form. So remember, in chemistry, lower energy means high stability. Okay? Low energy means high stability. And so C and D are more stable than A and B. That is why it is going to happen on its own. Now think about a boulder up on the edge of a hill versus a boulder at the bottom of the hill. Which has more energy? The boulder here or the boulder here? Well, the boulder here has more kinetic energy. So it's going to expand it by rushing and falling off the hill and comes to rest, right? So it's more likely to stay at rest on a flat surface. It's not going to try and roll on its own on a flat surface. But when it's up here in a very precarious spot, it is going to want to roll down because it has more instability up there than when it's down here. Does that make sense to you all? In endothermic reactions, the problem is these reactants are more stable than the products. Okay, watch where the reactant is. It is lower on the energy totem pole. You give all this energy, and you're creating products that are actually less stable. That's why endothermic reactions are really not popular. Okay, you're giving a lot of energy to form products that are actually less stable than the reactants. Now, there are many factors that affect the rate of reaction. I need you to know these, because these can be true or false. I could ask these as multiple choice questions, which tell you all of the following statements are true, except, those are the kinds of questions. There are 5 factors that affect the rate of reaction. Okay? One is structure of the species, how bulky it is. Second, it's the shape and orientation, whether the groups that need to face each other are actually facing each other. So imagine the thumb being a very critical part of this molecule, the thumb. So this is the orientation we want them to be bouncing off each other. What if this happens, right? Or that happens? Well, these are all ineffective until this happens. Do you see what I mean? So that's what it means by the shape and the orientation. If the molecules are not facing each other correctly, all the collisions are a waste. What about concentration? That's a given. If only me and Justin were in this room and we were trying to catch each other, it would take us a long time to bounce into each other, right? But imagine there were 100 people in this room. Would you likely bump into someone else? That's concentration. And you would likely, if you're running, let's say we were all 100 people running, chasing, imagine the energy with which we would knock each other around. We wouldn't knock each other down just because there's so many people, but we would certainly injure each other. Right? That's effective collisions, because by the sheer number. But if there are only 2 people running around and we're trying to avoid each other, we will avoid each other. So temperature. What happens with temperature? That happens to us too. Imagine when you say you have a hot head today. That's because your temperature is rising and you're angry. And that happens to reactions too. When the temperature rises, the molecules are colliding like this. So that's why hot water is so dangerous, because the molecules have a tremendous amount of kinetic energy in them. They are colliding vigorously. So when you pour hot water on you, it burns because all the kinetic energy slams and it has to stop. It's kind of like when a car, which is driving at 100 miles, snaps into, hits another car that is stationary. What's going to happen? It's almost death, right? But what if this car is moving and this car is moving? They both move, of course, they're moving this way, that's the end of the story. But if a car that is moving at 100 is hitting a car that is also moving, unlikely to cause as much damage. But what if this car is stationary, or a man is stationary, a person is stationary, and a car slams into you? All the kinetic energy transfers to this person that is standing. Same thing happens. When you pour hot water, all the kinetic energy comes to rest. But the amount of energy that is transferred is enough to damage your skin and your cells. So that's what burns are. Whereas when you pour cold water, what happens? They're not moving even in cold water. So you feel it, but it doesn't burn you. And that's what it is. Physical state. What if you take a cube of sugar, put it in cold ice? Is it going to dissolve quickly? No. Why? Because first of all, it's a cube of sugar, which restaurants love to torture you with, because it looks fancy, but you're storing away, right, forever. Whereas powdered sugars dissolve faster. Again, why? Because cubes, you have to first wait for it to fall into the powdered phase before it can dissolve, and all that takes a long time, right? So the physical state, a solid versus a gas, presence of a catalyst. The last one, if you have a catalyst, it'll make the reaction go fast, but a catalyst itself doesn't participate. So it's like, I don't know if you've ever had a moderator or a facilitator when you have sued somebody. The person in the middle is just mediating between the two parties. The two parties don't see each other. They're in two different rooms, and usually the mediator is a lawyer. He facilitates that you come to some agreement. But he has nothing to gain or lose. Of course he does, monetarily speaking. But he doesn't gain or lose anything as far as the case goes, right? So that's a catalyst. A catalyst can make things go fast, can mediate, but doesn't really participate in the reaction. Okay? So if I ask you all six, intuitively would you know the correct answer? Structure of the reacting species, molecular shapes and orientations, concentration of the reactants, temperature of the reactants, physical state, and a catalyst. Yes? Good. Believe it or not, folks, we are coming to the end of the semester. In less than 4 weeks, I will not be seeing you again. The semester is over. That means your third test and your finals and the paper are all due in the next 4 weeks. I know. So pace yourself. Brace yourself for the storm. Right? And for some of us, we're perpetually caught in the eye of the storm. We don't even see the storm until it just devours you. So don't be in that situation. I have to use those examples with my kids because they don't ever get it. Don't procrastinate. But they're very fond of procrastinating. Oh, I'll do it tomorrow. So that's my kids. Okay, structure of reacting species. Now let's go over each of these 6 states. Okay? Structure. What do we mean by structure? Well, if they're oppositely charged, are they likely to come together and collide? Okay, we have 2 positive charges. Are they going to collide? 2 positives repel. A positive and a negative collide. So the charge, if they're charged, you want opposites. That's when they're likely to collide. Yes? So ions with the same charge do not react. Because what benefit do they have even coming close to each other? Nothing. Right? Bond strength. Covalent molecules have very strong internal bonds. Those need to be broken. Molecular shape. A large molecule may obstruct. What is this? Thumb. We're tucked inside the molecule. What you have to do is open it up, expose it, and then collide. So you see all that when the functional group is tucked inside, it's obstructed. Then all the collisions are wasted. So only molecular collisions with the correct orientation will result to the product formation. Does that make sense? Okay. The rest of all this is theory, guys. No math. All this is theory. Okay? So the rate was generally increased with higher concentration. The rate was generally increased with higher temperature. The rate was generally increased with the phase of the substance. Okay? So rate increases as temperature increases. Is that a true statement? Yes. Greater kinetic energy increases the speed of the particles. Then they're likely to have effective collisions. The physical state of the reactants. Reactions occur when they collide frequently and with sufficient energy. So the gaseous, actually you may think the gaseous state is the best, but actually it's the worst. Because what happens in the gaseous state? It's hard, yes, they're spread too far apart, and it's difficult to bring them together. So believe it or not, solids are bad. If you keep two solids, they're not going to react because they are too compressed. Gases are too far apart. What's the best phase? The liquid. The liquid is the best phase. That's why most reactions take place in a solvent, like water or something. And what is your body made up of? Water. That's what we're made up of, water. Which is why, because all our biochemical reactions require a medium to work in. Okay, liquid state, they're free to move and yet close enough. Okay, so the liquid is the best, so keep that. That's a good question to ask, because we tend to think the gases are the best. Does that make sense to everybody? Very good. What about the catalyst? Well, the catalyst's only job, it does not undergo any change, does not alter the final product. But what they do is they give an interest. So look at this. This is how much time it would take for this reaction to take place. That's a speed activation hump. But what the catalyst will do is lower the time that it takes to reach the hump. Okay, the best analogy I can think of is how much time will it take you to climb this mountain? Let's say about 8 hours. Okay, and you climb, okay, so you have point A over here and point B over here. Okay, you're trying to get to B, and the only way in the city is to climb the mountain. So everybody climbs the mountain, and then one smarty says, I'm just going to build a tunnel. You see what I mean? So the smarty that builds the tunnel gets there faster, does less work. But did the mountain disappear? No. So you have to remember, catalysts don't make the mountains disappear. They just give you an alternate route. And that's where students make the most mistake. They think the mountain's gone. Okay? Build a tunnel. Got it? Excellent. Next. So the rest, this is all intuitive theory. Some students like it, some don't. Next we go to equilibrium. Equilibrium is all about, so what does equilibrium mean to you? Most reactions, when they start, they go into equilibrium. Equilibrium means forward and the backward reactions taking place at the same time. Most of the reactions never, ever go to completion. They go into an equilibrium, which is very annoying because equilibrium means you have unreacted reactants. You cannot push it to form all products. So equilibriums are difficult, but there is a trick to manipulate it. Now look at this. This is an equilibrium right here. So equilibriums we show with the double arrow. You see the double arrow on the equilibrium? We always show that. So when you dissolve sugar, actually, when you dissolve sugar in water, when you dissolve the sugar molecules, believe it or not, unbeknownst to you, because you don't see this, some of the sugar molecules fall out and another molecule goes in. So it's like I give you $10, you give me another $10. I give you a $10, you give me another $10. We're giving different notes to each other, but at any given time, if I ask you to show, you'll have the same amount of money as me. Does that make sense? But they're not all the same $10 bills. They're different $10 bills. Okay? That is equilibrium. So at any given time, it'll look like, oh, same number of molecules are dissolved, but there are different molecules that keep falling out of solution. We can see all this. That is an equilibrium. A continuous change is taking place without observable change in the amount of sugar dissolved. That is equilibrium. Did that make sense? Okay. Okay. This is an equilibrium. Watch. This is a very common reaction in the United States. Do you know what this is? This reaction is $1 billion, actually $7 billion industry in the United States. Do you know what this reaction is? It is the production of fertilizer ammonia. Okay, ammonia is a very common fertilizer substance that's used. It's a very interesting reaction. You take nitrogen gas, you take hydrogen gas, and you heat that to form ammonia. But the problem is the equilibrium. So for the industry that's making ammonia, They don't like equilibriums. What they want is to see this. All of nitrogen, all of hydrogen completely reacts. Watch. The language changed with a single arrow. With a single arrow, I don't mean any equilibrium. I mean that it all got converted to ammonia. Do you see what the language is with arrows here? But that's what everybody wants. But this is what they get. Okay? That is an equilibrium. Why? Because unfortunately, you have to nudge the equilibrium. It's a very common phenomenon. It happens in all reactions. It is difficult to get every molecule to react and form the product. Okay? So your job, okay, there is math. I take that back. Actually, there is math. You're going to calculate what we call the equilibrium expression, but they're very, very easy to do. Trust me. The equilibrium expression is, look at these, please, formula. It's a very simple formula. Okay, these brackets mean molarity, the big M. So in the problem, you will be given the big M. Okay? These stand for concentration. So it's concentration of the product times the concentration of the other product divided by the concentration of both the reactants. Yes? So what is that little a, little b, little c, and little d? What are those? What are those? They are the coefficients in a balanced equation. So if I were to write the equilibrium concentration for this, nitrogen plus 3 hydrogen gives me 2 ammonia, what would my equilibrium expression be? It would be the concentration of ammonia, yes, the product, divided by the concentration of nitrogen times the concentration of hydrogen. Yes? Now, don't forget, you have to raise these concentrations to the powers, which is the coefficient. So what is the coefficient in front of ammonia? So raise this to 2. What is it in front of nitrogen? Well, no, here, 1. And raise the hydrogen to 3. Does that make sense to you? So on the test, or in some of the examples we're about to do, you will be given the concentration, and I will ask you to solve for K equilibrium. Yes? So you need to know that K equilibrium is the concentration of the product divided by the concentration of the reactant. Yes? They're all molarities, and it'll be given to you as such. Just watch. The important thing is some rules that you have to remember. I'm sorry. The brackets represent molar concentration, which is the big M. Yes? All constants are shown as units less, so there is no unit for this calculation. When you finish the K equilibrium, it's just a number. Then, very, very important rule. Only the concentration of gases and aqueous solutions are shown. So, aqueous solutions. Concentration for liquids and solids are not shown in the equilibrium expression. What do I mean by this rule? So I guess we all understand this rule? We understand the brackets? Do we understand why all equilibriums are unitless? Because the moles cancel. But I think most of us have trouble understanding the last rule. Let me show you what I mean. Let me take generics. A, solid, plus B, aqueous, gives me 3C, aqueous, plus D, liquid. Can you write me the equilibrium expression for this? The rule says equilibrium expression, K, is equal concentration of the product divided by the concentration of the reactants, correct? Okay, now you need to pay attention to these guys, aqueous and liquid. So, even though you're tempted to do C times D, should D be included? It's a liquid. So you don't include D in the formula. Does that make sense? Now, should C be raised to 3? You divide by A and B. Should A be included in the expression? A is solid. You see how A is solid? So even though you are tempted to put A and B, the correct equilibrium expression would not have A in it. So it would reduce to just C cubed over B. Does that make sense? And that is very important to remember. Or liquids. All right, no solids or liquids. Okay? Okay, so write an equilibrium expression for this reversible reaction. It's just a question asking you to do that. You will look at them. Are these all gases? Then you know that you can include all of them. So you put HF squared on the top, and you divide it by H2 times F2. Does that make sense? Very good. Write an equilibrium expression for this reversible reaction. So what should I include? Should I include that? Yes, should I include that? Should I include that? No. That is why it's not here. Does that make sense? Divided by, should I include that? No. Should I include that and that? Yes. So that's why you have only those two. Does that make sense to you all? Why we leave the solid and the liquid out? Okay. All right, folks. Moving on. Interpreting equilibrium constants. Let's do the first problem. Calculating the equilibrium constant. HI is placed in a sealed container, comes to equilibrium, and the expression is given as that. The concentrations of all of the three guys involved are given to you in molarity, the big M. Yes? So, what is the K equilibrium for this expression? You put the H2 on the top and the I2. Do you agree with those two? Divided by HI but squared. Correct? Now plug in the number for H2. 1.72. Yes? Divided by multiplied by 1.72 and 0.54 squared. Is that making sense? Then you solve and you should get this answer, 10.1. So they're very straightforward problems, okay? So if you followed that, I'd like you to do these for me, please. Page 249, practice problem 7.8. Practice problem 7.8 and practice problem 7.9. And work with the group, please, if you want. 7.8 and 7.9. Practice problem 7.8 and 7.9. Practice problem 7.8 says, write an equilibrium expression. That's all you have to do on those. Okay? Do you get it? Write an equilibrium expression. That's all. There's no math to do in 7.8. Did you all get it? Okay, what did you get as, for 7.8, what did you get for the equilibrium expression? Yes? AG. Yes, AG plus. Minus divided by, should I have AgCl solid? There you go. Very good. So it's just going to be Ag plus and times Cl minus. Does that make sense? Yes. And for the second one, same thing. You're going to have PCl3 times Cl2. But you wouldn't have the PCl5 at the bottom. Does that make sense to you all, please? Excellent. Now for practice problem 7.9 on page 250. When is your next test, everyone? It's right after you come back from Thanksgiving. Yeah. Yep. Which one, ma'am? I'm going to extend the paper to, I can make the paper due at the same time as your poster, which we don't have very much time. Your last day that I'm going to see you is December 2nd. The finals is the next week, and you're 11 o'clock class. So for me, your final is going to be on Monday of the finals week. So for those who have a calendar, I think Alicia just has a calendar in front of her. December 2nd is the last day I see you for instruction. After that, you come directly, what is the Monday after that? The 7th of December, so in less than a month. I just told you, remember? In less than a month, I'm not going to see you again. Your class is over. So December 7th is your final exam in this class. Now we're going to finish 7 on Monday when I see you next week, and I'm going to start 8. So I could make the poster and the paper due on the same day, but I think that's a lot. How about we do the paper due on Wednesday before Thanksgiving? Is that fair? Well, remember, you should have been working on your paper all along, people. That's why I keep telling you, if you're going to wait till the last minute, no date is a good date. The 25th. Does that give you more time? Or do you want to do after Thanksgiving?
No, that'd be good.
Okay. So 25th.
And now it's the minute I came that you don't go.
No. I see you on Wednesday. It's not a holiday, people. I see you on Wednesday because I'll be doing stuff towards the test. And what I finish on the 25th will be on the test. Yeah, no. If I say I'll do it, I'll do it. I don't have a problem. I'm not here to penalize you. I don't want you to fail.
No, I was just making sure because I was thinking.
No, and I'm glad you brought it up, Georgia. So 25th sounds like good to me. Then you have the whole week to study, the holiday to study for the test, right? I'm trying to pace you. And then you have December 2nd when you have to do your poster. So if you're going to wait till after the test to wake up and smell the coffee on the poster, it's going to be too late.
That's something like for that.
Yeah. On Wednesday that I see you, we're going to have a poster presentation. Then we're going to start talking about the final exam and the test that you would have just taken. So I'm going to do 15 minutes of the test, giving it back to you and all that. We go over the answers. Then we have a poster presentation, a very quick 5 minutes, that's all. It's not like you're taking the whole class time. And then we just talk about the finals and we wish each other good luck and we part ways. Yeah, poster should be about, you know the little posters?
The plate, the nutrition plate. How are we supposed to do the nutrition? We have the guidelines.
Yeah, shall I talk about the poster right now?
Yes.
Okay, so has everybody understood how to do these questions? Why don't we continue with chapter 7 when I see you on Monday? Okay, let's talk about the poster. Okay, on the poster, you'll see those little ones that you get, little ones that just, I don't want a huge big poster. It has to be, I don't know the dimensions, but they're usually about this big, okay? And they are thin cardboard, not thick. They're about that big. You get those in Michael's. Yes? They can be any color. Here is what you're doing. You have to pretend like you're a nutritionist. And you're working with a partner on this, so hopefully everybody has a partner. Okay? You're working as a nutritionist. So this is your job. You have to come up with, okay, you're a nutritionist. Why don't I just write it here so for those who are not here, they can see it. So if you are if you're a nutritionist, how will you tell people to balance their diet, right? So you have to come up with a menu plan, a menu for 7 days of the week. 7 days. breakfast, lunch, and dinner. So you come up with breakfast. I wish there was a way to write breakfast, lunch, and dinner. And you need to include everything in the food pyramid, right? So everybody is aware, all that you get from Google. You need to include proper dietary things from the food pyramid so that you have a caloric intake of about between 1,200 and 1,500 calories a week. I'm sorry, a day. What am I saying, a week? A day. A day. Okay? You need to have this much calorie intake a day, about 1,500. You go over it, it's okay. So you need to include, and so, you know what, people said, oh, what if I want to have a snack? We're not complicating our lives by trying to include snacks and all that, but you need to have a good nutritional intake. So what if you were a nutritionist, and you want to appreciate that chemists are nutritionists, really. To be a nutritionist, you need to know chemistry. So you need to design a menu for Monday to Friday, right? 5 days. Let's not make it 7. Just give me 5 days. I'm good with that. Monday to Friday. How would you recommend your patients to consume a healthy, balanced diet that allows you to have 1,200 to 1,500 calories a day? Now, for that, Google is all you need because most of the nutritional labels on your food items are listed. So possibly what you should be doing is, if you're writing a menu for yourself, is look up the nutritional calories of the items you're eating every day. Yeah? So if you tell people have 2 servings, then you should be able to convert that to calories. How many calories is your patient going to get if they take 2 servings of fish, or 2 servings of meat, or 2 servings of fruit? Right? So you're doing that for 5 days. And I want you to be creative with your menu, okay? Don't make it the same boring thing every day. Include nuts, include fruits, vegetables, carbs, proteins, even some fat, even some dessert. People are not going to eat a menu. If you're a nutritionist, you're not going to sell a menu that has no fun in it. Okay, you can't tell people just salads for the rest of your life. This is just food. Oh no, that is lifestyle, right? What you're saying is lifestyle, and that's probably good, but we're just talking about a menu, okay? About 1,200 to 1,500, if you go over it, that's okay. But you need to don't give a 5,000 calorie diet to your patients, okay? Most of us don't need that much. Now, you should get started on this today, and then it'll be very easy. Yeah, students in other classes have had a lot of fun doing this. It's one of the best things. They enjoy doing it. You present for 5 minutes between the 2 of you. What I don't want you to do is stand here. All of you will come up with your poster up here, right? We'll get cake. So we'll put up Aaron's over here, Alicia's over there, and Justin's, and so on and so forth. But don't stand there going, on Monday, I want you to eat this. That's boring. You want to talk about it like a nutritionist and say, we included some elements of that, but on Tuesday we changed it a bit to say that, to have some, and this is what, and also, most important, which I forgot to even mention, is suggest the benefits of that food item to your patient. Because you're selling it as a nutritionist, remember? You have a tough job when you're a nutritionist. So benefits of your food items. Okay, so omega-3 fatty acids, or what is it that you want your patient to get out of it? Why are you telling them to take almonds? Or why are almonds better than cashews? Or why are peanuts better? So contrast. Compare contrast to foods, and it's a lot of fun to do because I think you will learn so much for yourself. You will learn a lot for yourself doing this. That's Steve. He wants to see an acid reflux design in it. If you include it, that's great. If not, I'm okay with that. Steve wants, because this project goes to both classes. Yeah, he's going to count this and I'm going to count it. That's why it's called the LC grade. He wanted you to put a little spin on it and suggest a diet for a patient with acid reflux. Yeah. Oh, okay. Did I say 2,000 to 2,500? You said 200 to 2,500. 200, no, I think 2,000. I mean, I must have meant 2,000.
You just said right now 1,200.
I said 1,200. I think 2,000 is too high. But like I said, if you want to stick to 2,000, I'm okay with that. 2,000 is still low. I think you might get it hard to be 1,200. 1,200 may be too low. How about we do 1,500 to 2,000?
Okay.
1,500 to 2,000 sounds like a right amount for everybody, for all, men, women, everybody.
Okay, so we're not going to do the 1,200.
No, I think 1,200 might be too low. Keep it 1,500 to 2,000. Okay? Now, you should have a partner in that you're going to work with to do this.
That way,